In this section, we're going to explore the discriminant of a quadratic equation. Now, the discriminant is part of something called the quadratic formula, which we are going to explore in the next video. We're not quite there yet. We want to just make sure we got this down first. So, a couple of definitions before we get into finding the discriminant. One is the roots of a polynomial. So, the roots of a polynomial are the solutions, sometimes called x-intercepts, zeros, to a polynomial that is set equal to 0. So we've got those interchangeable terms, roots, solutions, intercepts, or x-intercepts, and zeros, all the same thing. The discriminant, we got a wonderful definition there. It's a little bit wordy. Here's what I like to think about the discriminant. So in a quadratic equation, the discriminant, if the equation is in this form, and we'll talk about what that form is in a minute, is going to equal b squared minus 4ac. The form that we're looking at is that, if you notice, everything here is on one side and we have 0 on the other. Just like when we factored, we wanted it in that form so that we can pick out a, b, and c. Once I have those pieces, I can pick out the coefficients on those terms. So for x squared, whatever's in front of there, that's my a value. What's ever in front of the x term, whether it be positive or negative, is my b value, and the last term is going to be my c value. The discriminant is found by calculating b squared minus 4ac. So squaring this coefficient, subtracting 4 times this one, and then simplifying it from there. Now the number that we get will tell us a little bit about what kind of roots we have, what kind of solutions do we have, and more importantly, which method should we probably use to solve it. So looking at our first problem here, 1 and 2, we've already factored and solved for us here. It says, consider the first two problems whose solutions are given below. So we have this equation, x squared plus 4x plus 6 equals 10x minus 3. And that equals this. This is the part where I have to pick out my a, b, and c values once I have the equation set equal to 0. Once I actually solve it, though, if you take a look, we have the factors are x minus 3 and x minus 3. What that tells me then is we have a quadratic equation that has a double root. If I were to graph it, it would look something like this. There's our double root. Same thing with number 2. Once I bring everything over to one side, so in this step here, I can factor and then solve. And when I do that, I also get a double root. So this one, in this case, would look like this. Something to that effect. Okay, so what does that have to do with the discriminant? Well, let's actually calculate it. So once we have that step when we have the equal 0, we can start picking out our a, b, and c value. A equals 1, that's the number in front of x squared. B equals the number in front of x, which is negative 6. And c is our other number, which is 9. To find the discriminant, I'm going to take b squared minus 4 times a times c. So b is negative 6, and we're going to square that, minus 4 times a times c. Negative 6 squared is 36. And when I multiply these three terms together, I'm going to look at how many negatives I have. And between these three terms, the negative 4, the 1, three components of a term, I have a negative 4, a 1, and a 9. That's one negative number. I know that the result of these multiplied will be a negative number, and it turns out it's negative 36. My discriminant is 0. Same thing on number 2. I can pick out my a, b, and c values. So a is 1, b is 2, c is 1. 2 squared minus 4 times 1 gives me 4 minus 4, which also equals 0. It's not a coincidence that when I had a double root, when I factored and I had a double root, and then I found the discriminant, that I got 0. Because every other one that we've done here, the discriminant is 0, and we end up getting one root. That's a conclusion we're going to make, that if our discriminant is 0, we're going to get one, what's called a rational root, which means we can write it as a fraction. Whole numbers qualify because they can be written as fractions as well. But not everything's going to be a double root. We have some that are going to have multiple factors. So for instance, number 7 and number 8, when we factor those, we get two different factors, so we get two unique solutions. So in the first one here, we had 2x minus 3 was our factor, x plus 4. Those are our roots. X plus 1, x minus 4. Those are our roots. And if we were to graph something like number 8, it would look kind of like this. So x equals negative 1, and x equals 4. Not drawn to scale, just kind of a rough sketch. But you can see that's going to cross the x-axis in two places. Just like we did with the previous ones, we are going to find the discriminant and see if there's any kind of a pattern with these. You'll notice here in number 7 that a is now 2, b is 5, and c is negative 12. So I'm going to plug those values in. 5 squared minus 4 times 2 times negative 12. 5 squared is 25. And when I multiply negative 4 times 2 times negative 12, counting the negatives, I have two negatives, which will turn that into a positive. And when I multiply those, it ends up being 96, and that gives me 121. Interesting number, 121. Do the same thing on number 8. A equals 1, b equals negative 3, c equals negative 4. And so if I do negative 3, oh boy, negative 3 squared minus 4 times 1 times negative 4, that's going to give me 9, and then this part would become plus 16, and that's 25. Aha, so what I was interested about in 121 is I know that one's a perfect square, but so is 25. So when I've got two nice looking roots, so they're fractions maybe, whole numbers, something that's considered a rational number, looks like my discriminant part is going to be a perfect square. And it works out the same on all these. So every single one of these, this 256 is a perfect square, 400 is a perfect square, 4 is a perfect square, 100 is a perfect square. All of those solutions give us two nice rational, can write them as a fraction, roots. No radicals left over, nothing like that. So if we look at questions like 13 through 18, these are ones that when I calculate the discriminant of these, I'm not going to get nice numbers. And what I mean by nice numbers is perfect squares. I have 348, 52, 28, and so on. They might be simplifiable, that we can break it down further, but we don't get perfect squares. And that's going to be significant, as you'll see when we get to using the quadratic formula. And then we have ones where we have a negative discriminant. And that's something completely different. It doesn't matter if it's a perfect square or not. If it's a negative, that's a big red flag that something just doesn't quite fit what we're trying to do. Well, kind of hinted at it a little bit, but what does this all mean? Well, here's what this means. The discriminant will tell us a little bit about what kind of answers we're going to get. If we have something like b squared minus 4ac, the discriminant equals 0. That tells us that we have one rational root, and it's a duplicate. If we have something like b squared minus 4ac is greater than 0, so it's a positive number, that's key, and it's also a perfect square, what that means is that we're going to get two rational roots. And the reason this works out is if you look at some examples over here. The square root of 0, we know what that number is. It's just 0. The square root of 16, we know what that number is. It's just 4. Whereas this one here, if we have b squared minus 4ac greater than 0, but not a perfect square, well, what that's going to tell me is that I don't have rational roots. I have irrational roots. I'm going to have some decimals that never end. I'm going to have square roots in my answer. So something like the square root of 28 is an irrational number. Whereas if b squared minus 4ac is negative, it's less than 0, we can't do that yet. We don't know anything about imaginary numbers, and we're not going to learn that until a few years from now. But at this point, we're just going to call them two complex numbers. And like the square root of negative 12 would be an example of something that's a complex number. Regardless if it's a perfect square or not, if it's a negative value for the discriminant, that's not good. And we'll see in the video, why are we even referring to square root of that? Why does it even make a difference? But here's the nice thing. That discriminant can tell us what should we do. B squared minus 4ac equals 0 or greater than 0 in a perfect square. Factoring is the way to go. It should be easily factorable. If b squared minus 4ac is greater than 0 and not a perfect square, you can't factor it. So we probably should be looking for quadratic formula as a way to do this. Versus b squared minus 4ac is less than 0, we can't do those yet. So on questions like this, we're trying to figure out what are the nature of the roots. We're going to take our equation, put it in the correct form, find the discriminant, and say, okay, this is how many roots we're going to get, and the type of roots we're going to get. On this first one here, to get it in the correct form, we're going to have to subtract 2x and subtract 6, which gives me x squared plus 5x plus 1 equals 0. To find the value of the discriminant, I'm going to pick out a, which is 1, b, which is 5, and c, which is 1. So a equals 1, b equals 5, and c equals 1, and plug them into the discriminant formula. 5 squared minus 4 times 1 times 1. So 25 minus 4 gives me 21. That's my discriminant, but how about the nature of the roots? Well, if I'm looking up at my chart here, we're eventually going to not memorize this, but let's just look at it as reference. 21 is not equal to 0, so it's not this one. 21 is greater than 0, but it's not a perfect square, so that doesn't qualify. Then it would fit this category right here. A positive number that's not a perfect square is 2 irrational roots. In this one here, we're going to take away x squared and add 2. 3x squared minus 5x plus 2 equals 0. So there's our equation. And then we can take our discriminant. So a is 3, b is negative 5, and c is 2. And so negative 5 squared minus 4 times 3 times 2 is 25 minus 24. That's just 1. Based on my chart, greater than 0 and a perfect square would be 2 rational numbers. And so that's how it's going to work. We want to find the value discriminant, and based on that answer, what kind of roots are we going to get? And that's how we're going to use the discriminant. And again, in the next video, see where does this come from and why is it even important?